There are times when we're writing code where we want to declare a quick, anonymous function that combines a couple of short steps or has access to some local variables. C++, like many languages, has a feature that allows us to do this called lambdas. A lambda is just syntactic sugar for creating an anonymous callable object. A basic lambda declaration has three parts: the capture list, the parameter list, and the body. The parameter list and the body serve the same roles as they would in any other function declaration, and the capture list is something we'll get to in a moment. Here's an example of a super simple lambda. It takes no parameters and just prints a message out to the console. Here, we're storing the callable object this generates into a variable called f. Then we can call f to actually run our short little function, and we see the message get printed out. Now, there's another online tool called C++ Insights that's useful when you want to take a peek at some of the things the compiler does for you when it compiles your code. We can open this sample in C++ Insights with this button right here. Then, when we click this Run button, C++ Insights will show us the callable object that gets created from our basic lambda. So let's look at the code that it generated. The include statement gets translated without modification. Then you see the start of our main function. Within that, we have a new class. Because this class has an unknown anonymous type, but the compiler still needs to have a name for that type under the hood, we get this weird _lambda 514 type name. This lambda class has a couple of operators and functions defined on it. There's one that we're most interested in though, and that's the function call operator defined right here. Just like the lambda we declared, the function call operator is not taking any parameters. And in the body, we can see we're using the stream insertion operator with the cout object to print our lambda's message, which is exactly what we wrote in our body over here. These next two functions are for decomposing this lambda into a function pointer, which is something we'll talk about in the next video. Once we finish the declaration of that class, we're back into the executable body of our main function. Here we can see the declaration and initialization of our f variable, which has now been resolved to the lambda 514 type, and we're calling the default constructor of that type. Then we're using the function call operator on our f object with no parameters to call that lambda function. So that's how a simple lambda gets expanded into a callable object that we can pass around our system. But there's one more important part of lambdas that makes them super useful: captures. A capture is an external variable that we attach to our lambda. The code in the body of the lambda can use all of our captured variables. Each captured variable is added as a member variable of the callable object that the lambda creates. We can capture variables either by reference or as a copy. To capture a copy of a variable, we just need to add that variable to the capture list. And that's what we've done here. I've created a new variable x just to hold a little integer for us. In the lambda declaration, I've added x to the capture list. So this tells us that this lambda will be capturing x by copying its value. Inside the body of the lambda, we can now read the value of x and add it to our printout statement. And because x is part of the capture list and not the parameters list, we still don't need to provide any parameters when we call our function. Over in the expanded version of the code, we can see how that capture gets translated. Here we now have a private member variable for this callable object of type int called x. And the constructor for our lambda now takes in a value to initialize that x member variable with. But we still have our function call operator taking in no parameters and using the insertion operator a couple of times to print out the message that we specified. One important thing to note is that we actually are capturing x as a copy of the value when we declare the lambda. Let's go back to Compiler Explorer to see what that does. So here's that same code back in Compiler Explorer. When we initialize x, we give it the value of 10. That's the value that will be copied into our lambda when we capture it here. After our lambda is initialized, I'm incrementing x, so it now holds 11. We can confirm that by printing it out directly in main, and sure enough, we see the value 11 gets printed. Then we call our lambda and it prints out what it thinks x is, and it says x still equals 10. And that's because x still does equal 10, the lambda's version of x. There's two x variables here, one in the main function, and then the one in the lambda that we copied from the main function when we created the lambda. This is important, since any changes you make to a variable after you capture them by copy don't get reflected in the copied variables inside the lambda. Again, it's its own object with its own member variables. To capture a variable by reference, we put an ampersand in front of the variable name in the capture list, which is what I've done here. Now this is telling the compiler that it should be capturing x as a reference to main's x variable and not creating its own variable that copied it. Now what we can see is that we're still incrementing x in the main function, and when the main function prints out x, we still see 11. But now when we call our f lambda here and it prints out what it thinks x is, it also sees 11. Because we've captured x by reference, any changes we make to the original x variable get reflected in the lambda. It's important to remember that references in a lambda capture are still references. You need to pay attention to the lifetime of the lambda and the reference object to make sure you don't end up with dangling references. There are two ways to automatically capture all local non-static variables that a lambda body uses. These are called implicit captures. You can implicitly capture all used variables by value, or by copy, with the equal sign in the capture list. And you can implicitly capture all used variables by reference with a single ampersand in the capture list. I personally try to avoid implicit captures, because they can sometimes make it easier to end up with dangling references without it being obvious. But it's an option. When you're writing a lambda in an object, you can capture the object by adding this to the capture list. The lambda body then has direct access to all the members of the current object, as if it were a member function itself. It's important to remember that capturing this is capturing a reference to the object, so the lambda should not outlive the object it captures. Like any other function, lambdas can return values. By default, the lambda's return type will be deduced from the return expression in the body. If you want to explicitly specify the return value of the lambda, you can do so by adding an arrow with the return type after the parameter list. Lambdas are a super useful and powerful tool. Despite just being syntactic sugar for creating an inline callable object, it makes that process easy enough to actually be convenient and useful. Unfortunately, it also means lambdas can be easy to abuse and overuse. In general, you should try to keep lambdas short, maybe only a couple of lines long. If you find yourself writing a long lambda that does something significant, you should probably consider just making it a proper function. Really long lambdas quickly become a nightmare for the maintainability of your code. And that's all on lambdas for now. We'll see lambdas again when we take a look at the algorithms provided by the standard library.